Welcome, everyone. The following session, Calculus in the Quadrivium, Inspiring Wonder Before Graduation, will be presented by Mr. Tom Rosenwinkel, who's an upper school teacher at Memorial Lutheran School in Houston, Texas. Please welcome Mr. Rosenwinkel.
Thank you. So we are hearing a lot of CCLE history this week from the last 25 years. That's the theme. My history here is not very long, but I'm here to speak about calculus. And 25 years ago, I learned calculus. So I can take a few minutes to tell a story that took place far away from those conferences 25 years ago that Pastor Keyser talked about yesterday. The first time I taught calculus at Memorial Lutheran School, a parent really wanted to know how I learned calculus because I was the first from my high school's AP Calculus course to receive AP credit. So here's a more full answer to that question that I did not give to that parent. I learned calculus 25 years ago in a windowless storage closet. The government school did not have anyone else taking a fourth year of French, nor the resources to offer the course, so I went to a storage closet down the hallway. But they also could not work the schedule to allow me to take both English and band, and so English was struck, even though I don't play a band instrument. But there were no social studies department classes left for me to take because I'd taken all of them. So basically, I went to the storage closet for the rest of the day after lunch. And they gave me Enlightenment writings from Voltaire, Descartes, and Rousseau, and a very thick French workbook. And they sent me in the evening to a community college freshman composition course, about which I have very little memory. Now, since the whole school seemed to have forgotten about that arrangement before the end of the first day, I was very free for most of the time of my senior year. I took every old math book I could find into that storage closet, along with Tacitus for history and Gibbon's Decline and Fall of the Roman Empire. But now, as friends slowly discovered throughout the year where they could find me in the afternoon, the storage closet became a place where I could receive visitors. And to be clear, I was never visited by an adult. Friends from all high school grades quickly learned that they could skip by one class at a time just by slipping into the storage closet. No consequence. They brought tapes for the extra tape players from the French class, and I brought a deck of cards. And the sound from the shouting and singing did not seem to penetrate the walls or the door. One of my visitors was a graduate from the previous year, and he taught me calculus one October afternoon. Looking back, it might seem strange that graduates could float their way into a government school, into a storage closet the year after the Columbine shooting. Vince was actually hard to miss, too. He wore only orange clothing, a bright orange t-shirt and bright orange gym shorts year-round, and orange socks and orange sneakers. He was somewhere over 6 feet tall, with another 1.5 feet from his bright orange mohawk. His name was not actually Vince, but for some reason my mother could never remember his name and would only call him Vince, so I might as well use that name for him today. He was known for repeatedly explaining three things. First, that his house rested on cinder blocks, which was unremarkable in that township. Second, that he didn't smoke, which was remarkable because everything he touched would instantly smell infused with smoke from how thick it must have been from his parents in his home. And finally, he explained that he taught himself piano from nothing but sight reading in this thick book of W.C. Chopin and Beethoven classical romantic favorites. He would come to my home and play the piano for hours. He was very good, and I've heard very good, so I know he must have listened to great performances. So he's a very smart guy, and he eventually was one of the few people I ever met who left that township. He went to work for a book-selling company that used the internet in Washington State. He gave me the greatest insight I needed to learn calculus through independent reading. He explained how the pointwise values of a function's derivative could be used as a generator of itself up to an arbitrary constant or initial condition. It's the fundamental theorem of calculus as applied to dynamics of ordinary differential equations. He said that if I understood this from the beginning, then everything that I would read in the course would be clearer, and he was correct. What I found back that year, 25 years ago, and which has been supported through a variety of my own calculus teaching experiences from on and off in those 25 years, which I therefore believe finds its home in classical education, is that a deep study of the fundamental theorem of calculus really should be the entire focus of differential and integral calculus, and therefore should be stated early, supported gradually, and referenced throughout the year, rather than existing as a topic requiring algebraic and trigonometric prerequisites only reached as a culmination of the first semester of rigorous computational mastery. The more technically precise we can teach the language to express this theorem, which can be in fact done with little algebraic prerequisite and no trigonometry, the quicker and easier students will teach themselves the algebraic and trigonometric prerequisites they need. Then the chain rule simultaneously with substitution techniques for integration, the product rule simultaneously with integration by parts, and curve sketching simultaneously with Taylor's theorem. And this is not only my experience with a few students at Memorial Lutheran School. I've spent a lot of time in the last year teaching online, found this to be a motivating approach for adults and teenagers alike, regardless of their local national math curriculum. So before I move on, I will fix the slides. Okay. So now to go more quickly to my chronologically second formative insight. I'll need to go up to 2 years ago. So 25 years ago, I learned calculus. 20 years ago, I learned and began teaching all areas of computational and applied mathematics, up to courses commonly cross-listed between upper-level undergraduate and graduate levels, especially numerical analysis and partial differential equations. 20 years ago, I left a Lutheran education world that was different from this one for first a software company. And then 8 years ago, I recombined my software and mathematical careers to become a data scientist and AI developer. And finally, I'll say the second greatest insight I found for teaching differential and integral calculus came 2 years ago from a combination of Memorial Lutheran School faculty development readings, starting with the Clark and Jane book, The Liberal Arts Tradition, and also from reading Nicomachus in a reading group with many of you who are here today. And as other presenters have said, if you would like to join that reading group, talk to me and talk to Mrs. Mildred, Mr. Hahn, Mr. Mullen. There are many of us that are in this group, and it's good to have more members. So first in this presentation, I'll give some introduction to the Quadrivium, and it cannot be a full introduction, but I think I can give the Quadrivium just enough shape to find a place for calculus. Despite my typo in your conference workbook, the Quadrivium is marvelous. It is our marvel of it that can be either motivated or suppressed by the way we approach it. The Quadrivium is not the long march to calculus, to reiterate a helpful contrast one of our speakers used last year. Even in many classical schools today, the Quadrivium is studied as the long sequence of algebraic and trigonometric prerequisite skill masteries that must start in early grades, sometimes too early, and it may but often does not actually terminate in a calculus class before graduation. While some students are motivated to start early and move quickly through this mastery sequence, keeping a classroom together through it consumes time and resources. It does not always work in our common experience, and therefore sometimes entices boredom or worse. Now, like with Saxon mathematics, the most natural environment conducive to success within this sequence is the homeschool environment in which motivated students can work self-paced for individual mastery. Many can finish calculus before the end of 10th grade, in time for standardized tests in 11th grade and college and scholarship applications in 12th grade. Once I give the Quadrivium enough shape to find a place for calculus, I'll describe a shape for calculus and suggest a natural fit. And with remaining time, I'll give examples and draw conclusions and take questions. I want to acknowledge that the question as to whether the Quadrivium should be required before high school graduation or left for later is an open one. My case here only gives one support for one side of that question. My case here is that calculus finds a natural place in the 11th grade of a classical school, which allows for anyone interested in a STEM career to intensify their studies and compete for applications and scholarships their senior year. But more importantly, introducing calculus in the 11th grade of a classical school introduces the mathematical arts of the quadrivium through great texts to all students before graduation. So what should we know about the quadrivium? In general, it is the 4 mathematical arts within the 7 traditional liberal arts. In his Republic, Plato describes the quadrivium in his book 7, Education for Philosophers, not his book 3, Education for Children. He would precede a study of the quadrivium by childhood, which he defines as the first 18 years of life, and then 2 years of military service, so no one would be qualified until age 20. Quadrivium would require 10 years of full-time study, though Plato admits not much studying would actually happen during the first few years while recovering from the strain of military service. However, similar to his description of introducing blood during childhood to prepare boys for military service, Plato also says arithmetic and geometry and all the other studies leading to dialectic, and that's philosophy, should be introduced in childhood, though we mustn't exercise any form of compulsion in our teaching. Why, you might ask? Because a free man ought not to learn anything under duress. Compulsory physical exercise does no harm to the body, but compulsory learning never sticks in the mind. The prominence of the quadrivium in the education of the philosopher is due to its function on the allegorical path out of the allegorical cave for Plato, the conversion of the mind from a kind of twilight to the true day, that climb up into reality, which we shall say is the true philosophy. Only by age 30 would dialectic philosophy then be studied for 5 years before experience, responsibilities, and the life of the philosopher kingship would be ultimately attained. Now, the first art of the quadrivium is arithmetic. And arithmetic is the study of number. Our primary textbook for arithmetic is Nicomachus of Gerassa's Introduction to Arithmetic, in 2 books written about AD 100. In his first book, he describes the quadrivium of the ancient Pythagoreans. He grounds the concept of number in the distinction between unity and multiplicity. A multitude may be an infinite collection of individuals, such as stars or sands, but Nicomachus defines a number to be quantity set off from multitude. As the foundational art in the quadrivium, we will see that the ancient approaches to studying number were different from much of what is commonly found today in textbooks and teacher training programs. Plato said, studying arithmetic for the sake of knowledge and not for commercial ends draws the mind upwards and forces it to argue about numbers in themselves, and will not be put off by attempts to confine the argument to collections of visible or tangible objects. While today's common pragmatic and utilitarian approaches and objectives might be okay for children, according to Plato, they are actually quite distracting when it comes time to study the mysteries and majesties of arithmetical number. Similarly, reducing arithmetic, or any art of the quadrivium, to problem solving does not point the mind toward the eternal. Today we call number theory a field within mathematics, which fits within this liberal art. But also today's abstract algebraic theory of groups, rings, fields, ideal structures, and the like would find a natural home in the study of number, as would combinatorics. These fields are recognized today as important foundations for cryptography and scientific computing, but even these modern theories were not developed with applications in mind. As pure studies of number, I will call them examples of arithmetical arts here, but I will not call today's common approaches to arithmetic and algebra examples of arithmetical arts when those studies begin with the algebraic properties of real numbers. The algebraic properties of real numbers are indeed arithmetical, but the real number line itself only relates to classical number through 19th century completion properties, which had nothing to do with setting a quantity off from a multitude. It may be tempting to think that algebra would find a natural place as a study of number in a progression after arithmetic toward calculus, because solutions to algebraic equations are numbers or sets of numbers. However, algebraic equations are expressions describing abstract properties of numbers, not problems to be solved. Before lunch and over in the auditorium, Mrs. Mildred describes the linguistic nature of numbers and their expressions. In this presentation, I want to keep algebra and its symbolic expressions separate from the objects of those expressions, just as also Nathaniel Hahn discussed yesterday. The object of study of the arithmetical art of the quadrivium are what we today call the natural numbers, integral numbers, not the real numbers. While the abstractions of algebra certainly help point our minds to the eternal, today's common approach seeking real number solutions, regardless of their integral or rational nature, masks the majesty and mystery that Diophantus of Alexandria or Nicomachus of Gerasa would bring into our classrooms. Therefore, actually blunts our ability to think about problems and solve them. Children are rightly confused when there aren't 3.8 buses to take the whole school on a field trip. Their mother did not have 2.1 or even 2.3 children. Even if oriented negatively as well as positively or denominated as rational numbers. A classical study of number is to emphasize the discrete nature of the natural numbers and all their structure, which is their beauty as well as their utility. So many topics from algebra, such as factoring or the polynomial or the multi-digit arithmetic that we saw before lunch. Those are all excellent examples that belong to the arithmetical art of number. However, solutions to quadratic equations and a lot of other parts of algebra just generally do not. The next art of the quadrivium is geometry. Geometry is the study of magnitudes. Our primary textbook for geometry is Euclid's Elements, which is written very differently than Nicomachus wrote 400 years later. So for consistency of this presentation, I will give Nicomachus's grounding. The concept of size as the distinction between a unit and another magnitude. As multiplicities can be infinitely countable, Nicomachus describes magnitudes as infinitely subdivisable. A geometric number, best today expressed as a measurement, is, according to Nicomachus, a size set off from magnitude. We capture this with our concept of precision of measurements. We use instruments that have a limit to their unit subdivisions, but a pure measurement would be infinitely precise in the sense that the natural numbers could be considered infinitely countable. Plato actually lists geometry twice, once as plane geometry and once as solid geometry. Geometry is often characterized as number in space, and I think that is helpful in as much as Descartesian geometry can be described as objects in multiple numerical coordinates. Extending to any number of dimensions higher than 3 is a natural extension here, along with projections, as would be inner product structures such as angles, rotations, and trigonometry. These are the geometric operations that structure magnitudes, just as the arithmetic operations structure numbers. Just as numbers are the abstract objects of study of arithmetic, so are magnitudes the abstract objects of study of geometry. Describing this abstractness of pure geometry and its ordering of the mind toward the eternal, Nicomachus quotes Plato's Republic. You amuse me with your obvious fear that the public will disapprove of the subjects you prescribe if they don't seem useful. But it is, in fact, no easy matter, but very difficult for people to believe that there is a faculty or eye in the mind or soul of each of us, which these studies purify and rekindle after it has been ruined by other pursuits. The eye of the mind or soul, this eye, is more worth preserving than any eye or thousands of bodily eyes, since by it alone is the truth of the universe beheld. Those who agree with us about this will give your proposals unqualified approval, but those who are unaware of it will probably think you are talking nonsense, as they won't see what other benefit is to be expected from such studies. So the ancients understood that many would forsake the study of pure geometry for the thousands of material eyes today named STEM. Euclid could study abstract magnitudes with no other language than proof. But geometry should not be the only place we go to learn about proofs. Just like algebraic expression should extend to numbers and magnitudes alike, proofs and deductive reasoning should be seen and expressed in number and algebra as well as geometry. Just as not all things logical or deductive involve magnitudes, neither do all things spatial. Many spatially oriented visualizations describe magnitudes and directions, but many describe numbers and their spatial properties as well, such as when Nicomachus describes polygonal and various solid numbers. This distinction between number and magnitude is important for this presentation. So one day I found myself somehow a substitute Latin teacher. I found a calculus student studying Spanish, so I wrote this triangular array of numbers on the whiteboard, just in case she wanted help with her writing assignment on the exercise that I instructed before this session began. If you did that exercise, then you first came up with one of those 55 numbers, which can be proven abstractly according to two parameters. It's very upright to the point, and I did not bring a laser. The difference between the outer two digits, the greatest and the least, is I symbolized it with a capital delta, the Greek letter capital delta. And then the difference between the inner two digits as the lowercase delta. So there are differences, and there are two parameters. And according to those two parameters, you can arrange them so that the first capital delta gives the row of the triangle, and the lowercase one, the inner difference, is the column of that triangle. And there are a few technical notes beyond that, and that's about as symbolic as I wanted to get with this one, though there will be a lot of symbols once I actually start talking about calculus. Technically then, the notes though are that because of the way that they're defined, the capital delta being the difference of the outer two or more extreme numbers will always be greater, and that's what gives this array its triangular shape. And then when the lowercase delta is 0 and there are carries that have to happen, or regroupings, then that first digit will have to be decremented for that carry to happen. The other one that's interesting to note is if you happened to pick a 4-digit number that are all the same digit, then you would get 0, 0, 0, 0 when you subtract them. But otherwise, you would have gotten one of those numbers. And then as you repeat the process, it becomes more interesting. But for now, what should we know about the conclusion here? This is a spatial arrangement of numbers, but it's not this subject is not a geometric structure of magnitudes. It's an arithmetical structure of numbers, and it's proven abstractly and represented visually. Now I believe I've introduced the quadrivium enough to give a shape to find a place for calculus, but would like to complete this section of the presentation with a few comments on harmony and astronomy. So all traditional descriptions of the quadrivium include music. What should we know about music? Sometimes it's listed after astronomy, sometimes it's listed before. For today's presentation, I think what we should know about music is that it is a study of relative number or motive number, meaning number in motion or change in numbers. Sometimes music as a quadrivial art, and not at all as what most people mean today when they use the word music, it's characterized as number in time. And I find that characterization very helpful. As the difference between number and magnitude is that numbers are discrete and magnitudes need not be, a discrete sequence of pitches over time is the classical prototypical example of relative number, or music. The study of music included, in the ancients, the study of planetary motions, because cycles could be counted, and indeed they do mark the seasons. The study of music especially includes constants of motion, such as those found in Kepler's harmonic law, relating areas and times swept by a planet in orbit. Kepler describes, and others have talked about, the music of the spheres, or the harmony of the spheres. That's part of this ancient and through medieval liberal art. There's an interesting connection between changing numbers, such as pitches, and human sentiment, as in the Musica Humana described by Boethius in the 4th century. We can describe music as any structure, mathematical structure, connected to the ears, though Plato said himself that such things should be studied outside or abstracted from the pitches, stars, and seasons themselves. As a structure connected to the ears, I would say that today's natural language processing and large language models and many other behavioral predictive analytics in data science and artificial intelligence belong in this ancient and medieval liberal art, noting as well their connection between numerical sequencing with individual and social human sentiments. As much as we teach in Lutheran schools so that our children will be best prepared to listen to sermons, we should be concerned with this liberal art, understanding how numbers change in time, the way our minds and behaviors are shaped from such a study. And I'll say more about harmony in the course of this presentation, but not much about astronomy. Ms. Roundy will teach that in about 50 minutes in the other room. However, I believe she'll address the natural science as well as the mathematical art of astronomy. For completeness, what should we know about astronomy? If we think of 2D and 3D bodies in motion, we can consider them relative magnitudes or motive magnitudes, magnitudes in time or number in space and time. Spatial numbers in time would be an excellent characterization. Mathematical modeling and therefore physics and physical astronomy belong here. As such, philosophical debates of nominalism versus realism can be found and addressed here, and therefore probably also concepts of statistics, machine learning, and artificial intelligence in general. As the Pythagoreans and many before the scientific revolution reverenced astronomy, so does the 21st century raise scientific modeling and AI to clerical institutions. As music was described as mathematics connected to the ears, astronomy might be described as mathematics connected to the eyes. So computer vision fits well here. So it was most interesting to see how the lower grades, 5th and 6th grades, reacted and responded when these numbers were displayed on the whiteboard as they entered Latin class. When the exercise from before this presentation is represented visually like this, interesting patterns emerge. So if you look at the shading, the gray scaling, the darker the gray that I shaded this, the lower that difference between the two digits are. So from a difference of 2 between the extreme digits, down to, in the lightest ones, a difference of 8 and 9. And the colors, the grayscaling, forms nice L shapes. And then the coloring is for the lowercase delta, or for the difference between the middle digits. You can see that those colors also form interesting L shapes when the triangle is arranged in this way. And we can use those patterns. So what's not colored in this is the diagonals, which have their own pattern, and also this extra column, the special one with that extra decrement. So those patterns I put onto some different slide, but you'll see that when arranged in a triangle, starting from the middle and radiating outward, it is the same digits, and so you'll have the same results as you resort those digits and do a subtraction. And the destinations now are the shaded ones. And so the destinations, or the results of applying this process, they also have an interesting visual structure when arranged spatially. So here's that last column, the outline being the source, and then if you apply the process, the result forms a pattern that begins here with red, up to there for purple, and walks back down to there for orange. So those patterns can be used to determine what will happen if that process is repeated. As that process is repeated, well, there are two numbers that, according to those patterns, actually map to themselves. A 0, 0, 0, 0, if you subtract it, will result in itself, but also 6174. 6174 is today called Capricar's number, and that's why this was a game at a software company Christmas party. It's because that's very fun and interesting. That 6174, you get itself, and it's the only one out of all the 4-digit numbers. But knowing the patterns in the triangle, you can find, well, which ones lead to that, because they would be mirrored from the diagonal according to those L shapes. And so those are the ones that, if those happened to be your number that you chose, then you would have gotten 6174 right away. Did anyone happen to pick 6174? You did. Yeah, that's wonderful. Yes, we have a winner. You get to, if you're in 5th grade, that means you get to choose your partner. I put their names on the board and they loved that because they could do the subtraction, and it was a very fun exercise. So you can find the ones that lead to the ones that are one step away, and you could assign these a 2, and so I shaded them a little grayer. And you can just completely fill in the rest of the triangle to show that whatever your number was, first you would land in the triangle, because we already proved that out of all 10,000 numbers, you'll get one of those 55 on the first try. And then you can see where they flow or walk around visually. This is not geometry, this is number. But it's a visual representation, and it's proven, and it is abstract, but it's a beautiful structure. And so within 6 or 7 steps, you'll get to 6174. One 6th grader, related to that one, came back the next day and said to me that he couldn't find that triangle on the internet. He found a graph that related to the flow, that described the flow here. But this triangle is only inspired by thinking about this as number, visually arranged, and thought about as number in time. It's an excellent calculus problem. We've just now proven visually the 1949 result. Kepler was a number theorist that discovered this in 1949, 20th century. So I think the triangle is faster at understanding the proof. It's not very symbolic, and it's definitely more beautiful. So now, just as I did not give a full description of the quadrivium, but only certain shape that I needed for the presentation, I'll discuss some common and less common elements of calculus. So a typical first-year course in differential and integral calculus would focus on algebraic problem solving and solution methods and introduce a lot of new algebraic notation for derivatives and integrals through these topics. Limits, sequences, series and their convergence and divergence, slopes and tangents, trends, algebraic computational rules including linear rules, chain rule, product rule, quotient rule, change of variables of integration, integration by parts, partial fraction decomposition, curve sketching, graphing rational functions, extrema, and optimization, Taylor and Maclaurin series, numerical integration, and that's pretty much the table of contents of the course. So if you've taught it, you know those things, and if you haven't taught it, you don't. But while this base list serves as a minimal description of what we expect students to see or learn in a calculus class, there's actually a lot of room to ask not only what should we know about calculus, but what could we know about calculus. So to this question, I'll describe some things that I've done that I believe classical students can and should have from me, a calculus teacher at a Lutheran school. So the first thing I present in calculus, to recall from the introduction, is the fundamental theorem of calculus. But I do it first without any notation or definitions of derivatives or integrals. So I also don't do it on the very first day of school. While most textbooks will begin with a unit on functions and inverses, I use the month of August, our school is the first week, half week, and 2 full weeks on the calendar. I use it to establish as precise a language as possible from the foundations of mathematics to the concept of a function, culminating in an imitation proof writing assignment that a function is invertible if and only if it is bijective. So you'll see there are some symbols in there which we've taken a month to discuss, just a small number of symbols, but that's because math is a language, and we're starting with the language that they already know, which is English. Some of them might have come from a different school and might have had different backgrounds. But going through a writing assignment at the beginning and developing a precise language is very helpful. I have about 20 pages that I wrote myself just to read together as a class as an example of thinking and building definitions, specifying a domain of discourse as a binary true-false, from which statements can be made on sets and subsets, some reminders or primers on the basics of combinatorics, counting on unions and Cartesian product structures, relations as subsets of Cartesian products, ultimately then this definition of a function. So this is more precise than most scientists and engineers in STEM see until after their undergraduate times. But classical students are students of language and logic. So within the first few months, learning the grammar required and practicing writing epsilon delta definitions of limits and completion properties of real numbers can and ought to be expected as natural and helpful for all students, not extra for those who wish to intensify. So these are 4 lines that shape the mind and should not be a stretch goal after a heavy algebraic practice has been first completed. This is also actually a small number of symbols, but they're arranged and it's very highly structured. And it should take time, not just me putting up on a slide before you understand that. But it's central. If you know calculus, you know that this is actually very central and oftentimes just excluded due to lack of time in a lot of schools. So students who first understand the difference between discrete numbers and continuous magnitudes and the language describing them, those are the students who are best equipped for independent study, reading, writing, and practicing calculus with its intense symbolic language. So I've long been interested in the parallels between calculus of real numbers and discrete mathematics, and especially the parallels between Laplace transformations of functions and the generating functions of sequences. But understanding the classical distinctions between arithmetic of number and geometry of magnitude provides an excellent framework for presenting these parallels, beginning with the fundamental theorem of calculus. With a mind for functions and a good distinction between natural numbers, classical number, and the real numbers, which we might think as magnitudes, we can see that several natural examples of sequences and functions so these are familiar, and we can introduce them as change in time. So therefore, these are examples of the fundamental theorem of calculus. So first, a constant sequence, or a constant function. The differences of the terms of the sequence or the slope of any constant function is 0. With an initial value specified, the entire constant sequence or function is actually specified by extension. These constant sequences and functions make a family that we can label as degree 0. If a constant sequence or function is given to be the differences, then we find the study of arithmetic sequences themselves, or if the slope of a function is constant, then we get linear functions. We can call those the family of degree 1, and this requires no new notation for calculus. So these are fundamental theorems of calculus that are seen by most students before they enter a calculus class. I've rearranged them just a little bit, most notably, instead of using x, I try to use t to be consistent with the theme of time. I then introduce the summation notation with its index. Instead of n d's, it's d added to itself n times. And that's what multiplication has always meant. And then we can look at what if d is not constant anymore. If there are various differences, that's noted with the delta. And then last, we can look at generalizing a little bit more. Instead of starting from 0, start shifting or translating to another place on the set of numbers. So we have an interval, a summation of differences that constructs a sequence from a starting point and looking at the differences. In the world of discrete mathematics, this is called a telescoping summation. Telescoping summations are not always found in high school, but they work out very nicely. They're easier to learn than the fundamental theorem of calculus that we're used to, but that makes this an excellent way to introduce the fundamental theorem of calculus, especially to classical students who like to think rightfully about number as discrete. So then we can put the continuous version side by side with it and first introduce an integral notation that is the analog of the summation with its dummy variable. The concept of dummy variable becomes foundational to the study of calculus. And then instead of a constant slope, which we learned is m because of some French linguistic history before lunch, if it changes, if that slope changes over time, I just use a dot to represent that. A dot that depends on that time interval. So this is the fundamental theorem of calculus that we're used to seeing, especially when we move away from 0 just to a general interval a to b, or general place on the number line. So I don't actually start with this, but we get there pretty quickly before we learn all of what you would think of in a calculus class, which we then go through pretty quickly and easily because the notation and the language is there. And they've practiced writing some things. There's other interesting patterns then that we also use as examples before we really have abstracted it and are proficient with it. When the differences themselves are linear, we get an area, and that's in number as well as in magnitude. We get half of what Nicomachus called the heteromesic numbers, which is very fun to read and to practice. And it's the analog of the rectangle and the triangle that is the area under a linear function. So now we're using the notation of calculus, but we're not doing a lot of calculus. We're learning the language of calculus, and we're practicing translating. So there's one other very interesting one that is important and good to see and bring up, and it comes also from Nicomachus. Nicomachus did not have the language of Euler, Bernoulli, or Laplace, or any of those. After we said things got weird after the 16th century the other day. I don't think they got weird. We expressed things differently, but Nicomachus said that the geometric proportion has a peculiar property shared by none of the rest, that the differences of the terms are in the same ratio to each other as the terms to those adjacent to them, the greater to the less and vice versa. Still another property is that the greater terms have, as a difference with respect to the lesser terms themselves. And similarly, difference differs from difference by the smaller difference itself if the terms are set forth in the double ratio. In the triple ratio, terms and differences will have as a difference twice the next smaller. In the quadruple ratio, thrice. In the quintuple, 4 times, and so on. In our algebraic notation, we would do a close reading, and we would see lots of examples if you just look at the sequence of powers of 4, powers of 5. You'll find that we have this proportion, which is an excellent result, that the difference of the geometric sequence is proportional by the rate r, by the rate of growth of a geometric sequence. This is the same as in continuous time, like Euler's number. In fact, this is, if we subdivide and start to look at the relationship between the discrete and the continuous, this is actually the definition of Euler's number. If we could take all of calculus, a full year of differential and integral calculus at a classical school, and summarize it with one number, it would be Euler's number. So to the classical student then, all the classical population growth and decay models, present and future value models, stability and harmonic analysis, they're all at hand to be received or independently studied through these Euler exponential functions, which are an extension of what Nicomachus taught us 1,000 years before Euler. At Memorial Lutheran School last year, this meant that for about 6 weeks after Christmas, we got to study interpolation and numerical analysis from Newton's divided differences through cubic splines with their implications for numerical quadrature. And that's far beyond the Riemann sums typically found in a first-year calculus class. We then expanded the introduction to differential equations to include second-order equations for damped harmonic motion. One may expect that students who have learned how to read Nicomachus through Euler may also read Newton and Kepler through Bernoulli's notations. So this is another writing assignment example of it's using Bernoulli's notation. It's mostly language, but it follows the derivation from Newton's gravitational laws through Kepler's laws of planetary motion. It's about 3 pages long. This is just a snapshot of it. But it's excellent what you can do. And so that makes it a summary of Newton's Principia Mathematica of the late 1600s. When it comes time for college credit, we could take the assessment questions and study for them independently in a few weeks. And so like the common concern about what is the time that it takes to look at these things so deeply is that time can be made up. And of course, I had excellent students. This speaks a lot to the studiousness of these ones, but they could make up the time, and they had a great calculus class through that. Other examples that I don't have as snapshots on the slide, but the musical theme is revisited when resonance is described through the frequency of the forcing term matching the natural frequency of a system in damped harmonic motion. The themes of comparing the discrete with the continuous are reinforced when the general solution to a Fibonacci sequence is found through the roots of the characteristic polynomial, which happens to be the same characteristic polynomial as for the golden ratio. And finally, when the same differential equation is framed as a boundary value problem instead of an initial value problem, the discrete harmonic frequencies of classical music, with their ratios to the fundamental, can all be found in the continuous Fourier series solutions. So those studies are deep, like each one of those that I presented is rather deep, but they're not many in number. They can be studied much for a week or 2 at a time during the school year, and are broadly representative enough to free independent readers from any advanced studies upon commencement. Seeing the same mathematical arts describing planetary motion and harmonics of music theory inspires wonder and worship before graduation. So next is an example, a little more deep of an example, which I think we have time to get into, which is good. This is a kind of advanced calculus that I think actually requires not a lot of algebra. It does require reading, and writing, and translating. The most technical prerequisite to what I'm going to go into here is Euler's identity. So students would have seen Euler's identity in several grammar quizzes, but maybe even writing assignments. We would have spent a long time already understanding Euler's identity. But then when we write the differential equation, so this is Newton's second law of motion, that the mass and the acceleration are related to the forces acting on an object. We have a damping force that is proportional to the speed of travel, and as its opposite, its sum with the acceleration, it sums to 0 to balance. And it's also balanced with Hooke's law from around also the same time as Newton was working. When those are balanced, Euler and that exponential function gives us a theory that they would see later if they go on to those studies after graduation. But the algebra to this, with some distributive properties, brings it to a quadratic equation. So Euler called that his fundamental solution. And if we want to solve for the motion, to find how does the motion change in time under damping force and Hooke's spring law, we solve a quadratic algebraic equation to look at this at the solution to the differential equation. I like to use it as an occasion to talk about some different methods for solving quadratic equations here. that we might see in a classical school when we have authors from across the centuries, the best of all the centuries. And it looks different from what you could also find in the 20th and 21st century. You should know that what we see in our textbooks is not bad. I'm just trying to bring in the best from other places as well, so we can at least see them and compare them. A Diophantine transformation, which is excellent preparation for the U substitution of calculus. If they can learn from Diophantus earlier, then they will be better calculus students. They'll be already pretty good with those kinds of techniques. Reduces a quadratic equation to a leading coefficient of 1, meaning that there are two parameters. When there are two parameters, we can visualize things very nicely. Two parameters, a horizontal and a vertical axis. But what's more is those two parameters, when we complete the square, this is the algebra from 8th or 9th grade, Algebra 1, with a little more rigorous reading and writing for our students, but it's the algebra is from Algebra 1. We can compare the b over 2 squared, what is added to complete the square, with the nk that's already there, and we see that those are actually a sum or difference of two squares. It should look like a Pythagorean theorem. That's when I call this a square, this is really the square of the square root, but classically, this is called a geometric mean, which is still taught in most geometry classes still, but not all, everywhere. But classical students for Euclid and all of the Pythagoreans would be familiar with geometric mean. It's different from the arithmetic mean, and it can be constructed through Euclid. For this, then, I'm going to switch over to, I made an interactive visualization for this, actually, so that we can see if interpreting that sum or difference of squares on a coordinate system, which is not a Euclidean thing to do, it's a Descartesian thing to do. But you can put the b over 2 in one coordinate, and that harmonic mean, the geometric mean, the square root of the product. Those can be constructed by 7th graders with a good compass and straight edge. And you can see that the hypotenuse would be the plus square root or the minus square root. If I scroll a little bit, it will remind us of the equation from the slide. So when you complete the square, that's very tiny. I didn't see how it would look in this room. The solutions to the quadratic equation will have a plus or minus in them. That plus or minus can be constructed with the circle. So you can see the plus side and the minus side. And if I've accidentally reversed the sign of Hooke's, not accidentally, but on purpose, but like if one were to consider Hooke's law being reversed, so that a spring, instead of springing against the motion, would actually spring with the motion, the root of the quadratic equation would be positive. It's on the positive side there. And so that would be an exponential growth. That is the instability of motion when Hooke's law goes the wrong way. But we see through the mathematical language and the mathematical construction, the geometric construction, solutions to quadratic equations are not only algebra, they're actually geometric to a classical student. They're smooth, real numbers. When we fix the size, what happens to the triangle is that this becomes now a negative that is added. It is negative, so it's subtracted. Negative means subtract. We got that before lunch. As it's subtracted, then the hypotenuse is that b over 2. B over 2 is the larger one with its square has subtracted from it the square of the leg. And so it's that other leg of the right triangle that is the plus or minus, that bigger circle. And both of these then, when Hooke's law has the right sign, both of those are negative. which means that Euler's solutions are exponential decay. And that's what we experience in stable damped motion, exponential decay. We would even call this, engineers would call this overdamped. That's the lesson in engineering, is overdamped motion. In algebra, there's a discriminant that says that at some point when we learn it as b squared minus 4ac. This would be a visual depiction of that, because we're looking at the triangle. Like, what if that hypotenuse becomes shorter than that growing geometric mean, that leg that is growing as I increase the strength of the spring? When I do that to the strength of the spring, and then we have two negative numbers, and as they're both negative, they're at least the same sign. So they combine classically. That is they have the same sign, the same quality. So they do combine. They do add together. They add as the legs of the right triangle. It's the squares that add to get the square of the hypotenuse. It is still a right triangle, and this time, since they're both negative, the square root yields the imaginary number. And so these are the complex conjugate solutions that they see in algebra. In algebra, this would be only equations written, not visually depicted in this way. But this has implications for the number in time, because this is what we would call underdamped motion. Euler's exponential functions of imaginary numbers, or imaginary parts of numbers, can be combinations of sine and cosine. So that's a fun little thing. This would be an example that I will not talk about a lot. It's actually more of a counter example. So what I gave has a lot of concept to it, a lot of reading and writing, and a lot of imagination. That would be 2 months, what I just did in that short time. We don't teach like we present at these. This has been 5 months of content, and I've skipped a few months at a time. Like, this is good. But this is not what I would teach, at least not as deeply. This is what I call an example with a lot of algebra. A lot of calculus classes will see problems like this. These would be like at a magnet school where students are very competitively applying for scholarships, fellowships, elite college, selective college applications. These are good to do, but these are also the kinds of things that once the imagination is there, the wonder and the curiosity are there, and the motivation to go into that as a career and as a service, these are very good things to do, but also the algebraic techniques here, like partial fraction decomposition, or like the very odd algebraic substitution, that the problem itself does not look like it's going to be as involved as what the actual word is. This is one of the worst ones that I could have chosen on purpose. Instead of spending 4 hours a day in calculus, like they do at the magnet schools, I did actually have some students that figured this out. They're also smart students. They're very good students, but good classical students, this is kind of like chewing food. When I have a baby at home that wants to eat, I give the baby food, and the baby does actually figure out how to chew the food. It's messy, so it requires a lot of patience. But I don't actually have to teach the baby to chew the food. The baby does figure it out, and the baby eventually doesn't need as much help from me. Like, I do want to help the baby so that the baby doesn't always need as much help, but this is the kind of thing that is a grow into. This is not a place to start. And so I would say if calculus is exposed early, this could be in a second or third year of calculus, and students can still compete for those fellowships in a classical school. There's one last one on a place for trigonometry, but instead, I think we're close on time. I want to check that anyway, because I started this late, and so I lost that.
I'm giving you some bonus.
Okay, thank you for the bonus minutes.
I'm biased, I'm a math.
This is a construction out of Ptolemy's Almagest that gives a visual proof. This is geometry of the trigonometric identity for adding angles. This is an alpha plus beta. Together makes alpha plus beta. And Euclid gives us half of the angle from the circumference would be the angle, or the angle from the center would be double. And so we get altogether the sine of alpha plus beta. And then from similar triangles, Ptolemy gives us that we would get sine alpha cosine beta plus cosine alpha sine beta. The similar triangles are marked by color and hatches. So that's in Ptolemy, and that gives us the trigonometric identities. However, Euler's imaginary exponential functions, without any geometry, give us the same trigonometric identities. So learning trigonometry in geometry is excellent, but instead of requiring mastery to enter calculus, if calculus can be presented as its concepts and a growth in mastery rather than enforced prerequisites, we'll see trigonometry again in calculus, and we'll see it actually in a different way. One last quote from Nicomachus as we close. And that is, really close to the end. That is that every diagram, Plato, so this is Nicomachus, quoting Plato, who's actually probably not Plato. It's a weird thing. Probably this is Epidonius, because Nicomachus writes Plato to at the end of his 13th book of laws, to which some give the title the philosopher because he investigates and defines in it what sort of man the real philosopher should be. In the course of his summary of what had previously been set forth and established, adds, every diagram, system of numbers, every scheme of harmony, and every law of the movement of the stars ought to appear one to him who studies rightly. And what we say will probably appear if one studies all things looking to one principle, for there will be seen to be one bond for all these things, and if one attempts philosophy in any other way, he must call on fortune to assist him. For there is never a path without these. This is the way these the studies, be they hard or easy. By this course one must go and not neglect it. And finding the eternal in the quadrivium inspires us to study the quadrivium to prepare the mind and soul for philosophy. Like the trivium, where the quadrivium is neglected, philosophy and theology suffers. Just as the same virtues can be studied at various periods of history through circumstances of the times, not only in spite of those circumstances, mathematical structures like polynomials and sinusoidals are best learned when studied from a tour that finds them deeply from within the different arts of the quadrivium, regardless of previous experiences. So to summarize and conclude, here are some things you might take away from this presentation. Calculus, developed since the 17th century, is a great way to describe the wonder of harmony and astronomy. Inspiring wonder in the study of number and geometry motivates a deep understanding of the relationship between the discrete and the continuous, which forms an early foundation for the study of calculus, even if prerequisite algebra is missing. Despite the appearances, a classical treatment of calculus, extracting the best from the great works, will actually involve more advanced concepts than today's high school level STEM curriculum would give you. Mastery of the algebra and trigonometry required of STEM calculus can take years to build, but early exposure to the upper quadrivium, with calculus introduced through classical pedagogical principles, will motivate the necessary continued study and will be more effective than enforcing long and hard prerequisite mastery of dry algebra and trigonometry. So now, I do not expect that you will remember proving Capricar's result beautifully as an example of framing it in the quadrivium. But I know you will be interested to know that 10 is a special number. So no other base or number of digits yields the beautiful arrangement with a triangle, only the number 10. So I hope someday when you need it, whenever you find yourself at that time, you can remember to look at your 10 fingers, fold them in prayer, and thank our Father for making 10 a special number, giving it to our bodies and our minds today. Not because it is required for STEM or career, but that we can proclaim, how wonderful are all his works for us through all of our circumstances. Thank you.